Projectile motion. A projectile will be any object thrown in the presence of gravity. Gravity will be the force that affects the motion. We're going to ignore air resistance to simplify things. The important thing here is that the horizontal and vertical aspects or components of the velocity are independent of each other. So we're putting together the two types of motion that we've been studying for the past 2 weeks. The constant velocity motion, which in this case the horizontal velocity is constant. No acceleration. The acceleration is 0. There is no force acting in that direction to accelerate the object. But the vertical component of the velocity will be changing at a specific rate. It's the rate due to gravity, the acceleration due to gravity. It's negative 9.81 meters per second squared. Well, as you can imagine, there's nothing in real life that follows a perfect parabolic path. But a lot of balls that we throw, baseballs, footballs, golf balls, do approximately follow this path. Now, with air resistance, there's some complicating factors you'd have to mix in, but we're going to, once again, ignore air resistance. But this is kind of a motion map of, say, a golf ball being chipped onto a green. And let's make life simple for ourselves. Let's say that you hit or toss or chip a golf ball, basically, and it takes off in this direction. And we have a motion map here in which, let's say, snapshots were taken every second. So each little dot here represents 1 second time frame. So this would be the ball at 1 second, and then 2 seconds, and then 3 seconds it'd make it to the top point in the projectile motion here. So let's make, once again, life simple for ourselves. What we want to look at here are the components of the initial velocity. Let's call it v. But we have a v sub x, that's the horizontal velocity, and we have a vertical component of the velocity. We call that v sub y, the two vector components. Let's say v sub x is 10 meters per second. And v sub y is 30 meters per second. We're going to round a lot of things off here. We're going to assume the acceleration is negative 10 instead of 9.8. So let's say a is negative 10 meters per second squared. So what happens here is this. As this projectile flies through the air, it follows this path, and then the first ball right here at 1 second, what happens is the v sub x stays at 10 meters per second. But the v sub y is accelerated, and it slows down as you go up. It slows down to 20 meters per second. So if the initial v sub y was 30, after 1 second, v sub y is 20 meters per second. So the vector resultant of the 10 and the 20 can be computed. Actually, we should go back and compute the actual initial v vector. V squared in the initial case on launch was the v sub x of 10 meters per second squared plus the 30 squared. So this is the v initial of the initial launch velocity. And if you do the math here, it's going to be 900 plus 100. It's going to be the square root of 1,000. Square root of 1,000 is 31.6 meters per second. That's the launch velocity. That's the initial velocity upon launch. But at the 1 second mark, v sub, I'm going to call this v sub 1 for 1 second. So the initial velocity was 31.6, the overall velocity. But the velocity at 1 second, v squared, equals 10 squared plus 20 squared. So the v at the 1 second mark is going to be the square root of 500. And the square root of 500 is 22.4 meters per second. So it's slowing down, but only in the vertical direction, but the overall velocity is reducing because of that. So when the ball continues at the 2 second mark, here's the thing, the vector diagram is it's still going 10 meters per second sideways. It never changes because there's nothing working sideways. Gravity only affects the ball vertically, so it has a vector vertical component of 10 meters per second, but the overall velocity is in this direction. I'm going to call that v sub 2, where the 2 is the 2-second mark. So once again, v sub 2 squared equals 10 squared plus 10 squared. It's going to be the square root of 200, so v sub 2 is going to be 14.1. I'm doing everything to 3 sig figs. You could have gone to 2 sig figs. Meters per second. When the ball gets to the very top, we really don't need to do a whole lot of computing because the ball is no longer moving in the upward direction. It's only moving sideways, but once again, still at the 10 meter per second speed. So v sub 3 is 10 meters per second, just sideways. And now the whole process repeats itself on the way down. The ball speeds up, so it's going to have a negative 10, but I can indicate that with a downward arrow, of 10 meters per second, but the sideways speed is 10 meters per second. So v sub 4, that's the 4-second ball, is going to be the same as it was, but a different direction. V sub 4 is 14.1 meters per second. I'm a little out of space here, but as the ball continues, once again, sideways 10 meters per second, picking up speed in the downward direction, 20 meters per second. So v sub 5 is the same as it was for v sub 1, the 1-second mark, which was 22.4 meters per second. And finally, when the ball hits the ground, as it's hitting the ground, that's the spot right here I'm indicating, 10 meters per second, a lot of space here, hits the ground with a vertical speed of 30 meters per second. The velocity would be negative 30, but 30 meters per second. So it hits the ground at the same speed it was launched. I'm not drawing the overall vector here, but the actual overall vector would be 31.6 meters per second. Let me use a different color so you can see that. V sub 6 equals 31.6 meters per second. It's the same as the launch speed. So everything is symmetric here. But one of the key things to keep in mind and to look at is that the horizontal velocity is not changing. Whatever it started off to be, it's going to stay at that speed. So we're going to use that fact as we solve problems now. Alright, so we're going to solve problems dealing with projectile motion. So this is my poor diagram of a person standing on a platform. The blue thing is supposed to be his gun. And we're assuming that it's 3 meters to where the bullet or the gun is going to shoot. We showed you this in class where, in the theory is this: if you shoot a bullet sideways, perfectly horizontally, eventually it's going to fall to the ground. It's going to follow a projectile path. It never goes straight. Even when it first comes out of the gun, it starts to fall immediately. It's just that usually it hits something before it has fallen too far. So it looks like it goes in a straight line. I actually obviously can't even see a bullet traveling, typically. But the idea here is this. In part A, how long does it take to hit the ground? Well, it's the same time as if we just simply dropped it. But we're still going to use, now we're talking about the vertical situation here. Here's the initial layout that I want you to use in all cases. You're going to split the problem up into 2 parts, horizontal and vertical. Now, horizontally speaking, there's only 3 things to keep track of. We're going to keep track of v sub x, the horizontal velocity, s, and t. Because there's only one equation horizontally, and that's going to be v equals s over t. That relates v, s, and t. Vertically, we're going to have v sub I, v sub f, a, s, and t as we've used for the past several days with accelerated motion, because horizontally the bullet's not accelerating. Now here's the trickiest part about this problem. Filling in the different quantities. For example here, the 250 meters per second goes here. 250. Because that's a horizontal velocity. It's not a vertical velocity. The initial vertical velocity is 0 meters per second. That's the tricky part. Right? You're not throwing something straight down. It's just being essentially dropped, because this bullet's going to drop. It's being fired sideways at 250, but it doesn't have any initial component vertically. The acceleration is going to be negative 9.81 meters per second squared, and s will be negative 3 meters. The other thing is that this where it hits the ground, which is going to be part B, over here, is going to be your S sub x. I could actually use that subscript over here as well, S sub x. This S for the horizontal is Sx, the horizontal, x meaning horizontal as in x and y axes. But horizontal displacement, sometimes we call it the range, will be indicated as I have in blue right there. So what you can remember from class over here with the vertical part, if you have 3 of our 5 variables, you can figure out the other 2. So if we pick the right equation, in this case, let's pick the third uniform acceleration equation, which I wrote down. S equals v sub I times t plus 1/2 at squared. That's the generic form of that equation. But I plugged in blue the specific numbers for this particular situation where you have a displacement of -3, which is equal to v sub I, which is 0 times t. That cancels out. Will fall out of the equation. Plus 1/2 times the -9.8 times t squared. That's plugging in the quantities from this problem. Well, if you do the math here, t comes out to be 0.78 seconds. That's how long, even if you drop something, it's going to fall to the ground. Whether you fire it or drop it, it's going to take that much time to fall to the ground. Now what happens in these projectile problems is that's the connecting link between the horizontal and vertical. They're both dealing with the same time frame. So that number is going to go into my t, or the t here. So we've answered part A, but now we're going to use that to get to part B. So in the horizontal motion, the one equation we have is v equals s over t. And our v is 250. Our s is what we're looking for, s sub x, the horizontal displacement, divided by the time, which now we know is 0.78 seconds. So if we solve that for s, or s sub x, we get 195 meters. So that's the range, or the horizontal displacement when the bullet lands. That's our answer to part B.